Good afternoon. Can you guys hear me? Yes. All right, so what's the breaking news today? What's the breaking news?
Christmas is coming.
Christmas coming. But there's something related to it. What's breaking news?
Finals.
Oh, finals. So the midterm is graded. That's your breaking news today. Okay, so midterm is graded. You have until Friday, the December 7th. So don't forget that. To ask for a regrade. We'll regrade your entire exam if you ask for a regrade. So make sure there's lead error on our part, otherwise you lose your points, right? It's kind of a mean thing to say, but we're saying it anyway. Right? Most likely, what you have to do is to make sure that if you strongly feel that the problem is misgraded, you need to talk to a staff member before Friday to get a confirmation and see if you want to submit it for a regrade. Okay? And specifically pay attention to the points deducted. Okay, what type of things they're saying, okay, you didn't count this, you didn't count this, you didn't count this, so you lost those points. So you got a question there, back there. Someone behind you. Do you have a question? Oh, you didn't have a question. All right, so the mean is quite low compared to the first test, right? So, so I think the key thing is that where you are ranked in the class. That's the main thing, okay? Because there's always going to be a curve at the end of the semester. There's not going to be a curve for this one, but you can also see that there's a very high standard deviation, so that people at both ends of the spectrum here. Okay. Now, if you're interested in understanding what your situation is, I actually have your current grade with me. I can access it. You can stop by, but I won't email it to you, but you have to make an attempt to come by. You from outside, I might be able to tell you what the current grade is. Current grade, that's okay. So right now the midterm 2 is not on the system, so I only have the grades based on midterm 1. So that might be a little bit higher now, it's a little bit lower, right? So that's. But I'm assuming that the midterm 2 was hard. Maybe the final exam is somewhere in between. Okay, I think midterm 1 is like high 80s for the midterm, for the average, and this is 50s. Probably in the 70s would be the final. I'm just guessing, okay? So the difficulty level would be somewhere in between. All right, any questions about this? Okay, so the key thing is to plan. Okay, right now this is the time for you to plan and see what type of a grade you want, what you have to do to get that grade, all that stuff. Okay? So going forward, you have one programming assignment and one written assignment, and the final is a written final again. So this means you have to be able to solve things on paper. Right? How do you do that? You will practice a lot of those things. And so as we go, we will try to do some of that within the next few days. All right. And also I will ask you that, when you take notes and, go home, read the notes again. If you take class notes, don't wait till the final week to read them, because typically you kind of don't understand by that time, right? If you take notes, it's clear, but then you forget. So if you reiterate that tonight, that you take notes and you look at it tonight, it might help you retain the knowledge. You have a question? Say that again. One standard deviation. Yeah. So that's one standard deviation. That's very high. Right? Compared to the mean, it's almost half of it. It's not a good thing, right? So this means that there's a diversity, but there's people on both sides of the grading spectrum. Okay? So ideally, standard deviation should be low, and the mean should be high, so that most people are sort of gathered around the middle, right? Around the median or median. Okay. All right. So these are the announcements. I think I don't want you to forget any of these deadlines. You should put that on your calendar schedule and make sure you do the second part of your project as soon as possible. It is due December 12th. There's no extension on any other time, so you just have to do it. If you don't finish by this time, it's not going to be graded. But my advice is to submit it, because you can, I don't think there's any limit to the number of submissions. I guess that's this one. Yeah, so I think it's still 3 submissions, but try to submit soon. And then final assignment is released now. It's under written assignment. So that's also due the same day. So you have to kind of manage these 2 within the next 9 days, right? Today's 3rd. All right, so schedule it and do it. I would ask you to do the project first because that's always going to take time. And written assignment, you will write something and submit it. Here's the final exam date, December 14th. It's about 11 days. If you have any conflict, you should email. Written assignment 5 is about searching and sorting. That's what we're talking about this week and the previous week. You have to submit the answers in a PDF file called assignment5.pdf. So ask someone if you don't know how to make a PDF. Okay, so you have to make sure that it's named like this. If it's not named like this, then you reject it. Following instructions is very important. And also when you upload your file, you have to click the submit button. If you don't click the submit button, then it may not submit. Obviously, it won't. When you close the computer, it's gone. Right? How do you know it's submitted? You should receive an email for each submission. You have unlimited number of submissions, so try to, as you finish, just try to submit it, so that you have unlimited number. We will grade the last one. Okay? And don't submit the last minute. That's always advice, not to wait till the last minute. Any questions about the 2 assignments? Okay, this is all you have to do, right? Then your final exam, then you're done, and you're certified as you will be an expert Java programmer. Like, you can get whatever job you want. No, that's not true.
Just drop out. Yeah.
Right? You still have to do more computer science. You want to be an expert, right? Okay. So the thing to solve in assignment 5 is to trace code, count operations, and sort of write pseudocode. You're not writing real code. This is a written assignment. How do you find queries have no common elements, things like that. So just pseudocode. And also notice that there's a problem with a 2D array problem. So you most likely will see 2D array problems in the final exam. So you need to understand that you will never test it out. Now let's take a look at what we did last time. So this table is very important. And what it says is that the insertion sort, we only look at best case and worst case here. Okay, it says that the insertion sort in the best case is linear. It runs in very fast. Okay, it's proportional to the number of things in the list. But in the worst case, it would run in the quadratic time, n squared. Selection sort, on the other hand, behaves the same way, whether it's best case or worst case. It doesn't matter. All right? So that's why people prefer insertion sort, because you hope that your best case are close to the best case. So it'll run fast. Okay? There's an extra column added here called extra array. Why is it there? Because the next sorting algorithm we're going to talk about will require another array. Okay, when you write insertion sort and selection sort, you don't need another array to kind of shuffle things in the same array and get it done. Okay? So let's take a look at recall insertion sort and selection sort one more time and count the operations. So let's start with selection sort. So let's take some random array. Okay, so we have 2, 1, 4, 3. And I'm going to count the number of comparisons that is needed to sort this array using selection sort. Okay, does anyone remember what you do in the selection sort? What do we do? Yeah, well, you guys know, right? Yeah. Find the max. Okay, so we find the max. Now, how many operations? This is n equals 4. Right? You have 4 things in the array. How many operations you need to find the max in an array of size 4? How many comparisons? Yeah? It's going to be 3, right? Because you only have to compare these pairs, 3 pairs. So you can find the first max in the array by doing 3 comparisons. Once you do that, then you swap these 2, right? Now you have to focus on an array of size 3. Okay, we are not going to even touch this in the selection sort after we put the largest one at the end. How many operations do you need to find the max here?
2.
Okay, you need 2, right? You have to compare 2 pairs to get the max. And so we need 2 comparisons to find the max. Okay? Now, in terms of n, you have to write in terms of n more generally. What is 3 related to 4? If n is 4, what is 3? N minus 1, right? If n is 4, 2 is n minus 2. So more generally, we talk about these number of operations in terms of n. Okay, so once we do that, we say, okay, I found it, but I don't have to swap anything. Right, then I'm going to focus on a simple array of size 2. Okay, at this point, how many operations do you need to figure out who the max is?
1.
Only 1. Right, at this point, you're going to make a swap. And so the max is in the right place. Only 1 operation. Are we done? We have to do more findings. Now we're down to an array of 1 element, right? So that's got to be the minimum in the array. Okay, therefore the total number of comparisons is 6. For this specific example. All right? Now, let's do the same problem with insertion sort. By the way, this is n minus 3. If you have an n things, you will go all the way down to 1 and stop. All right. So insertion sort, let's take a look at insertion sort for the same array. How does the insertion sort work? Okay, we assume that this is sorted, right? Then we try to insert 1 into that array. So how many comparisons do we need to accomplish that?
1.
Only 1, right? Yeah, only 1. So comparisons, number of comparisons, it's going to be 1. And then after you do that, you will have this. Okay, now we have to try to insert 4 into this array. How many comparisons do we need to accomplish that? Only 1, right? Because as soon as I compare 4 to 2, I know I don't have to do any more. Right? If this is bigger than that, because this sorted, this got to be the highest one. Okay, so you just have to do 1. All right? And, we don't, so after you do that, you will have this array, which is sorted. So notice that the array is getting sorted from left to right, as opposed to right to left. That one, right? Then we want to insert 3 into this array. How many comparisons we have to do? 2, because we compare 3 to 4, we know that's not true. We compare 3 to 2, now we know, okay, 3 got to go here. So we'll do 2, and then we will insert 3 into the array at the right place. And we got this. Okay, so in the insertion sort, the number of total comparisons is 4. Right? So you can see that even in this example, selection sort took 6 and insertion took only 4. Right? Okay. So what is the best case for the insertion sort? When we talk about best case, what type of an array are we talking about? The array is already sorted. Right? So imagine, you apply the insertion sort into something like this, 1, 2, 3, 4. Because each time you compare to the first one and say, okay, I'm done. Compared to this, I'm done. Compared to that, I'm done. Right? So you only do 3 comparisons before you know you don't have to do anything. right? That's just one comparison for each insertion. So the best case for the insertion sort is that the array is already sorted. What is the worst case for the insertion sort? It's reversed sorted, right? Because it's reverse sorted, it's a problem because if it's reverse sorted, let's say you have 4, 3, 2, 1, right? This requires one comparison. So you got 3, 4. And then you try to insert 2, now you need 2 comparisons. So 1, 2, right? So you will get, continue here. So you will have 2, 3, 4 after you insert 2, right? And then when you try to insert 1, you have to go 1, 2, 3. Right? So you will get then final array 1, 2, 3, 4. Okay, so if you had a reverse sorted array and then you try to do insertion sort, the number of comparisons is as bad as this one. Right? Selection sort. Okay, so selection sort is always bad. Right? Because selection sort, no matter what, it's going to do n squared comparisons, whether it's best or worst case. So you can see that the selection sort is the same for both cases. All right? Okay, any questions there? That's an example of how to count things and add them up and figure things out. Okay, sorting is really important. Yeah, as you can imagine, sorting helps us do things faster, right? It's much faster to find something in a sorted list than an unsorted list. Because if you have sorted lists, you can do binary search, which is log n time you can do something, right? Now, the Java has this utility, so let's suppose that we define some random array, and then we call this, we write code like this, arrays.sort. Okay, if you do that, what the Java will do is arrays is like a class of things, sort is like a process, a method, a sorting method. It will sort the array for you. Okay, in other words, going forward, you're not going to write your own sorting algorithm to sort something, okay? You will use Java sorting algorithm because it's proven to be correct, right? You won't have any bugs, okay? Now the question is, what does Java use to sort things? It turns out that the Java uses merge sort, something called merge sort. It doesn't use insertion sort, it doesn't use selection sort, but it could use insertion sort in some cases, so I'll talk about that. But for the most part, it uses merge sort. There's a reason for that, okay? Because the merge sort is the most consistent, fast sorting algorithm which doesn't really care about the input data. So this way, Java doesn't have to worry about, you have a sorted array, unsorted array, randomly sorted array. It's going to do this, perform the same way. All right? Okay. So what is the motivation for this sorting algorithm called merge sort? All right, so let me give you an example of that. So here's the idea. This is the major idea. After that, it's all recursion. So let's say that we have 2 arrays. Okay. We call this A, we call this B. And what do we know about A and B? They are already sorted. Okay? So these 2 arrays are sorted. Okay, what we want to do is to write a method that will merge the 2 arrays into one array of sorted array. Hence, it's called the merge sort. Okay? So the basic idea of merge sort is just merging 2 sorted arrays into one array. How do we do that? Well, let's think about this. Suppose I have a pointer to the first array called I. That's like the index that runs through I. Then I have another index called J for the second array. Okay? Now, what I'm going to do is, I'm going to start writing elements in order into this one, picking one from either one, depending on the situation, okay? So I'm going to keep a pointer called k here. So I have three ijk are the sort of index controllers, okay? So here's my algorithm, which is very simple. I compare a sub I to b sub j. Okay, so I will say if a sub I is less than or equal to b sub j, which is true in this case, right? And that means I will find the minimum of the two, which is 1, and write it here. Okay, in other words, this is what the code will look like. If a sub I is less than or equal to b sub j, then c sub k get 2. A sub I or b sub j? A sub I. Right, because a sub I is the smaller one. Right, so I'm describing the algorithm, I'm also writing the code at the same time. Okay, so we will organize things later. So if a sub I is less than b sub j, then I write to this one a sub I, c sub k. Okay? After I write this, I have processed this one. So I need to move my pointer to the next one, to I. Okay? How do I say that here? I want to go to the next I. So this code is not complete, right? Yet. Because I processed one of them, and I want to move the I to the next index. How do I do that? Yeah? I plus plus, so I equals I plus 1, whatever you want, right? What else I have to do? I also have to move the k to the next one, right? Because I have to be prepared for the next processing. So I'm also going to say k plus plus. Right? So I'm moving this index because, right? Okay, now so now what's the next comparison? I'm going to compare a sub I to b sub j. Right? This is j. I haven't processed these elements, right? So this guy is still there. Now a sub I now is bigger than b sub j. Okay? So that gives me the next case. What can I do? What do I do if a sub I is bigger than b sub j?
C of k is equal to
Which
A.
one I pick? Do I pick this, b sub j, or a sub I?
B sub j.
B sub j, right? So I write the 2 here. Okay? So in other words, I will say what?
C sub k is
C
equal
sub
to
k equals
B sub j.
b sub j. Right, so the C sub k gets the b sub j. What indices do I increment?
J plus plus.
Yeah, so I need to move j here. So I will increment j plus plus.
K plus.
Okay, and also I have to move k here. Okay, so I will also increment k by 1. Okay, that's the basic code of merging, right? So let's continue that process. So now I think I covered both cases, so there's no more to consider in the code. So I'll just do the process here, right? So next time I'm going to compare a sub I to b sub j, who is smaller. A sub I. So I process that and put it here. So c sub k gets a sub I. Okay, that code will still work, right? And then I move the I to the next one. Now I compare a sub I to b sub j. Now this is the guy I want to process, right? Because I always get the smaller one. Then I put the 4 here and move the k to the next one. So I process that. Compare again, a sub I to b sub j. Obviously j always moves forward after the process, right? So in this case you have, you gave a little perturbation, it's going, okay. I don't know. Yeah, I just touched it. Maybe it's a haunted blackboard, I don't know. Who knows? Yeah. All right, so what, now what, 5 and 6, so I will process 5. Okay. And I move now I here. So now I ran out of one array. Right, there's nothing to do there. Do I have to compare anymore? Yeah? What? No, right? You don't have to compare anymore. I know all I have to do is just copy 6 here and copy 8 here. No comparisons needed. Okay, so the number of compares you need is, let's talk about that next, okay? So notice that if I run out of one array, I can just copy the other array without doing any comparisons, because I know both arrays are sorted. Okay, that's your merge algorithm. All right, let me ask you this question. Now, if the size of A is n over 2, and size of B is n over 2, right? Let's suppose that they are equal size. How many comparisons do I do to get to create my C array, which is sorted? Total comparisons needed. In terms of n. I mean, you can take this context here if you want, right? Now, every time I do something, if I compare something, how many elements do I write to C? One element, right? And eventually I have to write n elements into this. And therefore, how many operations do I need? N things, right? So the number of total comparisons is of what we call linear, big O of n. Okay? So given two sorted arrays, you can merge them into a single array in linear time. Okay, linear time. Linear time is good. We'll take linear time any time, right? So linear time is okay. Quadratic is not okay. Right? I'll give you some examples of that. Okay. So the code that I was trying to write here, sort of like pseudocode, let's call that pseudocode. In fact, it's here. Okay, this is a real implementation. You don't have to know this implementation of the merge process. Okay? So you don't have to know this, you don't have to know how to write this, but you have to understand the algorithm. You don't have to know the details of this algorithm. Okay? So how does it work? It takes an array A and it takes what we call an auxiliary array. So in other words, this you can call the C. C is what we call the auxiliary array. Okay, that's C. All right, so what it does is first, it will copy all the things from A to the auxiliary array. So it's like a little bit different from what I did here. It'll just copy everything here and then go back to the A, right? It goes back to the A. So the way it's working is that, the K runs from low to high. Now the low would be, when you start, the low is going to be 0. Okay, high is going to be n minus 1. Okay, so because we want to process the entire array, right? And this is assuming that I can compute the mid, and it's assuming certain things. It's assuming that the array segment from, so here's what we're doing here, okay? So we have low, and the mid, and the high. Okay? Now this is mid, and this is going to be the mid plus 1. All right, so the first array is this part, and the second array is this part. So, and we assume that this is sorted and this is sorted. Okay, and then we try to merge the two into a single array. So that's what this code does. So you could see that there's a lot of similarity between what I was trying to do here, right? If the auxiliary j is, I think you can kind of map the code I have into this code here. The only difference is that the k here, I incremented at each point, but I could just increment it here in the loop. Yeah, like a while loop, that's what I could do, right? So I could do one increment of k. And then, what are these two lines? So again, just understand the code, but not really all the details. What is this saying here? This line. If I is greater than the mid, what does that mean? What is I? I is this guy, right? If it goes beyond mid, that means I have processed the entire array, left of it. Right? Then it's asking you to copy the rest of the J array. See, that's what it's doing. And this means I've ran out of the right array, because J has become bigger than I. In that case, I'm asking the algorithm to just copy it, just like we did here, right? So we just copied without comparing. So those two conditions are these dealing with one thing runs out before the other one. Okay? All right, now let me talk about merge sort. That's not merge sort, this is merge. Because this is assuming that the two arrays, two halves are sorted. But we know that's not true, right? In general, we don't have that condition. Okay, so what I'm going to do is this. I'm going to show you this merge sort applied to the merge algorithm applied to create the merge sort. So let's start with a bunch of single numbers here. So let's say you have 9, 4, 1, 3, okay, 2, and 5. We add 2 more here. We add like 10 and 6. Okay, let's assume that we have 10 arrays of size 1. Okay, in fact, but this is, if you can also think of this as a single array which is unsorted, right? Yeah. It's just that happen to have 10, 6, 9, 4, 1, 3, 2, 5. But for the understanding, we would just think about it. Are these guys sorted? The array with just 10 and the array with just 6? Yes. Sorted, right? So let me apply the merge algorithm that I have into create one array of size 2, which is sorted. Right, so I'm applying my merge sorting to these two. Let me do the same thing here. Because these are both sorted, I could apply my algorithm to get one array of size 2. Right, I merge two arrays of size 1 to get one array of size 2. I can do the same thing here. Okay, 1 and 3. So that's the merge. And then I will merge these two guys to get 2 and 5. Okay, do you see where I'm going? Right, what's my next step?
Merge
those. Merge those, right? Now I got 2 arrays of size 2. They are both sorted. And merge them using my algorithm. So I will get the 4, 6, 9, 10. Right? I just merge them. Okay? And I will do the same thing here. I will merge these two sorted arrays of size 2 to create a sorted array of size. Now you might ask, how do I do that? Well, it's already there. This is the, I will use that, right? That's why you have low and high, because I can apply to any part of the array. That's why you have low and high and mid, all that stuff. That's why this is all, these parameters exist. Okay, so what's my final step? I have 2 sorted arrays of size 4. And then now I will merge them to create one sorted array of size 8, right? 6, what's the next one? Is it 9? Okay, so if you think about this process, I can build it bottom up. Just keep repeatedly apply my merge procedure here to different lows and highs, right? Within the same array. So I can do that. Now you might ask, okay, why is merge sort better than insertion sort or selection sort, right? So let me try to explain that to you why. Okay, now, how many comparisons do I have to do to get from here to here? Total. Only one, right? How about from here to here?
One.
One. Here to here?
One.
One. Here to here, one, right? So I did a total of, I guess, 4 comparisons, right? In that level, to get to that level. But if I want to go from here to here, how many comparisons do I have to do? Because I have to now do, because it'll be like, it's some proportional to n, right? The size of the 2 arrays. So it will require 4 operations for each one. Okay, 4 operations and a total of 8. Okay. Now obviously I don't have any more, but you can say that this you can believe this hopefully, that each level I only have to do at most n operations, right? No more than n. So each level I will do n operations. And the question is, how many levels are there? Okay? So you will see that if I start with, if my array is size 8, how many levels do I have? I had to go 1, 2, 3, right? 3 levels. What's the relation between now 8 and 3?
2 to the third.
What's that?
2 to the third.
Yeah, 2 to the third is 8, right? 2 to the third is 8. But there's another way of saying that. We are saying that 3 is in fact log base 2, 8. Right, 3 is log base 2, 8. All right, so I'm going to claim this following. I'm going to claim that if I have n things, here I have 8 things, okay? So to merge sort n things, okay, I need to process how many levels? Log base 2 of n. When n is 8, it was log base 2 of 8. Okay? So in other words, if I had 16 elements, I will only process one more. Right? If I had 16, I will only process one more. Log n levels. Okay, and each level takes at most big O of n operations. Okay, therefore merge sort is what?
N log n.
It's n log n. Okay, so the merge sort is n log n. Okay, so why do we care about n log n? Right, it's still log n log n. Right? To understand why we care about n log n, let me show you a chart. So let's say n. Okay, let's deal with like 2 to the power 10. That's about 1,000 elements. 1,000 elements here. Million elements would be 2 to the 20. This is million. Okay, roughly 10 to the 6. What is billion? 2 to the 30 is a billion. Okay, roughly 10 to the 9. And a trillion would be, what is trillion? Trillion would be at least 2 to the 4. So this is trillion. Okay? Now let's take a look at n squared. If n is 2 to the 10, what is n squared? Exponent rows, 2 to the 10 raised to 2, right? That's 2 to the 20. Right? If n equals 2 to the 20, what is n squared? 2 to the 40. 2 to the 60, right? You raise means you just multiply the exponent by 2. Okay, this would become 2 to the 8. Right? Is 2 to the 80 big? Very big. Okay, it's really big. On the other hand, if you look at n log n, okay, if n is 2 to the 20, log of 2 to the 20 is 20. Okay, log of 2 to the 20. And if n is 2 to the 40, log of 2 to the 240 is what? 40. So it's 40 times the number. This is n log n. Okay, this is 2 to the 60 times 60. Okay, this one, sorry, thank you. Sorry. Okay, so n is 2 to the 10. Times log n is 10. Right? In this case, n is 2 to the 20, so it's 2 to the 20 times 20. And if n is 2 to the 30, then I have 2 to the 30 times 30. That's log n. Okay, this is log n. If n is 2 to the 40, so this is 2 to the 40 times 4. Right? You can see as n gets large, the difference between those two. Right? 2 to the 80 is huge. But 2 to the 40 is probably okay. Right? I don't know. We'll see. Okay? But you can see that, I mean, this is really big compared to that. Okay? Now, let's do like a experiment to show you how fast the merge sort actually runs. Okay, so here's the code. You will get a copy of this. I think, in fact, this is already there. So what I'm going to do is, okay, so you can see that my code that I use for the merge sort, I didn't talk about the merge sort algorithm. If it's recursive, I'll wait for that. Okay, you can see the merge code is here. It's the same code I showed you. And I need a merge sort to do the sorting because I have to keep merging, right? So that's where this second merge sort comes in. And then what I do here is that I take some argument from the command line, generate an array of that size, and I also notice that I create an auxiliary array of the same size. Okay, and then I will run the merge sort on this random array. This is a random array, and see how much time it's going to take. Okay, so we'll do an experiment to see what's going to happen. Okay. All right, so I'm going to run the merge sort. So I'm going to say Java C, just to make sure that I haven't changed anything. Okay, so toss. Do that, and then I will run the merge sort with, let's give it like 1,000 elements. These are 1,000 random elements in an array. 0 milliseconds. Let's give 10,000. 2 milliseconds. Okay, let's give 100,000. 23 milliseconds. Let's give 1,000,000. 142 milliseconds, right? Still like really slow. Milliseconds like this, like a tenth of a second right now. Okay, let's do it what is that, 10 million? It's 10 million. It's about a second now, 10 million. Let's do 100 million. Okay. About 1.17 seconds, right? All right, now you can see that even if I run a billion things, which I was never able to do with the insertion sort or selection sort, I will get an answer. What? Oh. What does it say? I ran out of heap space. What does that mean? That means I ran out of memory because I can't put billion integers into my memory space. How big is billion integers? Big, right? Because each integer is like 4 bytes. So you're talking about 4 billion things. What is 4 billion? There are 4 gigabytes? That's 4 gigabytes. Okay, to store this array, I need 4 gigabytes. I ran out of memory. Okay, so this shows you the limitations of computing, right? Okay, so it's an error. But I have been able to run this sometimes, okay? Because sometimes if I have resources, this means that maybe my computer is busy doing other things. Maybe it's playing games without me knowing about it, right? So it's using the resources in there. Okay, so you can see that but let's do this. Now I want to do a comparison, okay? So let's do Java C searching and sorting. So this program, what I'm going to do is I'm going to, this one here. So here, this is this program is the comparison program. So I'm going to compare insertion sort to the selection sort to the merge sort. Okay, so I'm going to compare all three to see how they work. So let's run this comparison algorithm with, let's do 100,000 elements. Okay, so the insertion sort took 856, selection sort took the same amount, but merge sort only took 8 milliseconds. Okay, let's go to, is that a million? It's a million, right? And is that 6 zeros?
Yeah.
So that's a million. So let's see what happens. I don't know, we might be here for a while because insertion and selection sort, it's trying to sort a million things, right? We'll come back to it. We'll take a look at that. Okay, now comes the real fun part. At least it should be fun. Okay, what is the fun part of merge sort? We wrote the merge, that wasn't too bad, it was an iterative solution. Now comes the real merge sort. Okay? Notice that the merge sort is recursive. Right? By now, you're very comfortable with recursion, you love recursion, right? Yeah. You apply recursion to everything in your life. Is that true? And when your girlfriend or boyfriend asks, do you love me? You said, well, that's a very difficult question. Right? Let me think of a divide and conquer algorithm for solving this, right? So you apply recursion. You said, love is very difficult to solve. Let's break it up. And let's break it up. Let's break it up. Okay? And then, by the time you go through that, your girlfriend or boyfriend will say, you're a nerd. Right? And, you're out of the hook. You're off the hook. Right? Okay, so recursion can help save you. Okay, that's what I'm saying. I've done it myself, so don't worry. It works. All right, so what is merge sort? All right, so recursion is intuition. Okay, so the recursion, I think a lot of people tell me recursion is hard. Sure, it's hard, right? Because it's not intuitive to the human beings. Humans we think iteratively, right? We think like, oh, I'll do this, then I'll do this, and then I'll do this, then I'll do this, right? How many of you think about, breaking up things to make it simpler? Right? Maybe if you break it up, there are people who can think like that. You have to train yourself to think like that, right? So when you actually see the algorithm here, it's fairly simple. What it says is this. Okay, if I want to merge sort the entire array, so here's my algorithm, merge sort the left side and merge sort the right side, right? Okay? So what will this give me? Let's assume that this is how you think recursively, right? So you don't want to think about all the small things. Okay, so you say that, oh, here's my left array and here's my right array. What by some magical means, I will sort this using merge sort, and I will sort this using merge sort. So what's the next thing I have to do? Just merge them. Okay, then all you have to do is merge the left and the right. Right? That's the kind of intuition you need to understand the recursion. Recursion says, I don't really know how this is going to be done. Obviously, when I ask, so let me show you how you might see this, how you might see the application of this algorithm. Okay, so here's how it's going to work. Let's say you have some random array. Let's take a simple one, okay? So I want to merge sort this, right? So I want to merge sort this array. Then it says this. It says, well, to merge sort this array, you have to merge sort the left and you have to merge sort the right. So I'll break this into two problems. So merge sort the left array and then merge sort the right array. Right? Because I don't, so this is how the recursion will work. Okay, merge sort the left array, merge sort the right array. And in the recursion, what happens is go back to the same thing, right? So it will say, oh, okay, it will go from left to right. Left to right. So what will this say? Now this is another merge sort problem, right? You break it into merge sort the left, okay, which is 5, and merge sort the right, which is 2. Okay, let me not even worry about that, because what this will happen is it will keep calling left, 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 right? But when does the recursion stop? It will stop if the high is less than or equal to low. Okay, that's when you return. But let's see what high and low are, right? So this is low, and this is high for the original array, and this is low and high for the second array, and the low and the high are the same here. Right? Each one has their own low and high, right? Because you see, each recursive call, notice how it works. You start with low and high are these, but notice each recursive call you said low to mid. This is the left side. Mid plus 1 to high is the right side. Okay? And this condition now, high is less than or equal to low, high is equal to low now. It's met. Right? Now, it's going to go to the merge sort part. Because in recursion, these things keeps calling until you reach the end part. Okay? And now it's going to say, oh, okay, I'm going to merge these two guys. Because I can't do any more recursion, right? So I'll create this array. 2, 5. Right? Can I do this now? No, not yet, okay? because I have to do the right one. The right one creates another set of things. So the right one will say, okay, you have to merge sort 4, and then you have to merge sort 3. So now I can say, okay, this is the same as low equals high, and I will create this. Okay? And now we got this situation. Now it's going back to that case and say, well, when I did this, I called the merge sort, but I didn't merge, right? So now it's the time to merge. So you create the merge, and you do the merge, and you get the 2, 3, 4, 5. Now, if you really want to understand this, you can say something like this. You can say what I really did is the following. How does the recursive calls work? Okay, so it's a tree. You have left and right. Okay? So notice that this guy called left, and that left called its left. All right, so the order things get done is that it'll keep calling left until there's no more left. So the first thing to get processed is this one. Okay? Once you cannot do left, see, this guy created a left and a right. Right? If you do the left, then you must do the right next. Okay? And if I do the left and right, then I will do this one here, right? Okay? And then, so, because I can't do this one yet until I do this one, right? What's the next thing it will do? Which branch? Because remember, you go, in this case, you're going to the right, but in the right, you're also going to the left, right? Make sense? Yeah. So this will be the 5th one. The 4th. Because you have to go right, but they go all the way to the left. And once I do that, I will do this. Okay? And then I'll do this, and here's my final thing. So if you actually look at the stack of evaluation, this is the order it gets done. It goes all the way to the left, come up, go to the right, come up, go to the right, and go to the left, come up, go to the right, and so on. So when you go to the next course, we're going to talk about these tree structures, and you're going to be using this kind of recursive thinking to traverse trees. Because if you're going to traverse a tree, how are you going to do that? You go all the way to the left, and you cannot go left, you go to the right, and then you come up and try to go to the right again. Right, by doing this type of, so this is actually a traversal algorithm. Okay, in fact, you will, if you really want to understand this, you can think something like this. Let's suppose I have a expression I want to evaluate. 2 plus 3 times 4. Okay, so I can create an expression tree like this. Hopefully you understand what I'm trying to say, right? So the root is the sort of the operator, 2 plus, because I know I have to do 2 plus 3, then 4, right? So the way this gets executed is that you do 2, apply the operator, gets 3, that becomes, 2 plus 3 is not 6, right? Gosh, I've got to go back to my elementary school again, right? It's a 5. And then you take 5 and do this, do that. It's 5 times 4 gives you 9. And so if I do this left root right, you will get the you will get this evaluation. Okay. Anyway, things to come next semester, right? It's going to be fun. All right. So how fast is the merge sort? So this is an example of a random array. We already talked about that, which is similar to the example I have on the board. Okay. Let's go and see whether that thing came back. Huh? So we put something to. Hopefully, I didn't run out of space. Came back. Okay, so that's for million entries. Okay, for the million entries, the insertion took 200 milliseconds. selection took 242 200 seconds, right?
Yeah.
200 seconds. So it took 200 seconds for the insertion sort, took 242 seconds for that, but for the merge sort it's 94 seconds. You can see that as the number n grows, things are getting really good with the merge sort. Okay, as long as you have memory to run it. Okay. All right, so merge sort, you understand this part here. So how fast is merge sort? Okay. Now, this is a chart that was done like 10 years ago. Okay? The chart compares a laptop that can execute 10 to the 8. What is 10 to the 8? It's about 100 million. Okay, so it can do 100 million compares per second. Okay? 100 million compares per second. And a supercomputer can do, what is that, 10 to the 12? It's a trillion compares per second, okay? So you might think that there's no real difference between 100 million and trillion, okay? But there is when it comes to n squared. So if you do insertion sort, okay, with a home computer, with a billion things, this computer will take 317 years to sort. Okay, you can do the math. It's not that hard to do because we know how many compares it does, and a billion is like 10 to the 9, right? 10 to the 9 squared is 10 to the 18. So what this is saying is that even if you do 10 to the 8 compares per second, to do 10 to the 18, you would need 317 years. Okay? Right? And then, but if you do merge sort, billion things will be done in 18 minutes. But for the experiment I ran, how much time it took?
94 milliseconds.
94 milliseconds, right?
Yeah.
So my computer is much, much faster than this table says. Right? I didn't even take, this one says 18 minutes. Right? Actually, my computer right now is like a supercomputer. It's kind of almost instant. Right? So within like, what, 10 years, 5 years, things have become so fast, right? So we have gone from 10 to the 8 to probably the level 10 to the, so your computer probably can process what trillion compares per second. Okay, so that's how many compares per second your computer can do, right? Is that enough? Have we reached the max?
No.
No. We want faster, right? Why do we want faster?
Better games.
Do we have to sort more things? No, right? What else it can do? What are the hardest, most difficult problems we can solve? This won't be on the final exam, okay? So don't worry about it. Just take it easy. The hardest problems, weather, right? Predicting weather is very difficult. Right? It requires so much processing so fast. The other problem I would love to solve is the traffic problem. Right? It's a big, very complex problem because all these stupid humans are creating all these traffic jams. And so I'm kind of waiting for the self-driving cars. Right? If you get self-driving cars, I will predict that you could have 0 wait time. Right? Because everything is going to be so coordinated. And nobody's going to press on the brake because they got a text message. Right? You know, that's how the most traffic jams are. So you can imagine how many billions you will save, how much time you save, and you can enjoy your life more, right? So there are very difficult problems to solve, and that requires a lot of computing power. Okay, and actually I'm teaching a class next semester called Data Science, which is about big data. Okay, so we're going to talk about some of those difficult problems, and I don't think we're going to solve them, but at least talk about them, right? Okay, so if you compare sorts, now we can add another thing to this chart called merge sort. Okay? Now the nice thing about the merge sort is the best case and the worst case is still n log n. Right? It doesn't matter what the best case thing is because there's really, n log n is so small compared to n squared, you will take it. Okay? You will take it n log n. And now this makes sense because I need an auxiliary array to perform the merge sort. So the only drawback in the merge sort is that I need an extra array. How big is that? Actually, when I did merge sort with billion things, okay, 4 billion, for the original array, I need 4 billion bytes. Right? Because each integer is like 4 bytes. So 4 billion bytes is 4 gigabytes. But I need another array about the same size, so I needed 8 gigabytes in my space. That's why I ran out of space. Okay, couldn't sort it, right? What's the solution?
More space.
How much more space can you get, right? What's the solution to the sorting problem? In fact, you know, this sorting is very, very important. It's not just sorting, but the I'm just taking a little bit of time to chit-chat today, right? Talk about the computer science and the sort of fun part of computer science. So if you're majoring in computer science, maybe you think, okay, I made the right decision. But if you're not majoring in computer science, maybe you want to think about it a little bit, right? Anyway, but that's your decision, yeah.
Did you try to split up the billion into smaller segments?
That's correct. I think that's what I would do. Okay, so if I have like 10 billion things, I would choose 10 machines in the cloud to sort them, separate. And then what sorting algorithm do I apply after each one is sorted?
Then you could do...
I can just merge them, right? I don't have to sort them anymore. I can just merge them into one big array. Okay? So in real life, when you have to deal with so big data, like so much size, that cannot be done even in a supercomputer. There's not enough memory to do it. So you can distribute the computing to many computers. In fact, sorting is a nice problem to solve in parallel, right? Because if I have, n things, I'll divide them into 10 n over 2 chunks, and then sort each one separate. And then it's a merging problem. Merging is easy. You just merge, right? There's no sorting. Okay, so the big sorting algorithms are done by just merging these small things. Small means that it's still there, like 10 million things long. The other sort of interesting problem in computer science is the encryption problem. Right? You know what that means? Encryption. Right? When you go to say for example, when you send an email from your phone, your message gets encrypted, right? So that no intruder can read it. Okay, it's all math. Because what it does is, it will actually create an integer with 400 digits, right? 400 digits. How big is an integer with 400 digits? That's 10 to the power 400. Right? What's the maximum digit you can keep in a computer? Maximum integer. If you have a 32-bit computer, it's 2 to the power 32, which is about 10 to the 9. Okay, so it's about a billion. So you can only keep about 9 zeros in a regular computer. But no computer can hold 400 digits. Right? So what this problem about the encryption is that you can break all the encryption. You can take a 400-digit number and factor that into 2 prime numbers. And that's impossible to do in trillion years with the current methods we have. Okay, that's why your card and all the things that you carry still work and secure. Right? They know it's you, right? Because you have a private key and public key. All right, anyway, that's all fun stuff about the sort of, but there's a lot of math. So if you're really interested in computer science, you have to learn a lot of math too, right, along the way. Because without the math, because if you think about computers, it's just, a bunch of digits, right, numbers. Even if you have characters, they turn into a number. If you have a A picture, that's a bunch of numbers, right? It's not a picture to the computer, it's just a bunch of numbers. All right. Okay, so next week, that's our planning. Oh, actually, before next week, we have to talk about this week, right? So we have to finish this week. So this week we will do binary search recursively. So again, recursion comes back. And on when? Wait, today's what? Monday. Okay. So today's Monday, so Wednesday we'll do that. And next week we have 2 classes, so I want to make a decision here, right? I can do one and give you guys a break. Right? The Wednesday class, there's no Wednesday class, then you got the reading period and all that stuff. So what should we do on Monday? Review. A review. Okay, so let's do that, right? So our plan is we will finish all the things that you have to know by Wednesday, and then Monday is a review day, and then Wednesday you're free. Okay.